Hi, I'm Chris, and in my last video I parameterized the HP class module and renamed it to FP class. When the code was the HP class module, the module was only able to identify the data type for 16-bit binary floating point numbers. The new parameterized FP class module is able to operate on all of the supported IEEE binary floating point types. In this video, I'm going to parameterize the HP mol module, making it into the FP mol module, and discuss how I automated testing for the 16, 32, 64, and 128-bit IEEE binary floating point types. Like the FP class module, the code discussed in this video is available from GitHub. See the comment section for directions on downloading the code. Now on to the actual code. Unlike my previous source code releases, the Git repository has multiple versions of the FP mol module, and I'll be discussing each of these iterations in the course of this video. By following the directions in the comments section, you can examine the initial commit of the FP mol code. The first change is a prerequisite for parameterizing the HP mol module. The module now uses the FP class module and passes in appropriate parameter values. Remember that the module needs to communicate to the FP class module the number of bits needed by the exponent and significand fields of the data. The second thing to point out is that I've renamed the module from HP mol to FP mol because it's now capable of performing multiplication for all of the supported IEEE binary types. Its predecessor, the HP mol module, could only operate on binary 16 operands. Beyond renaming the module, there are two categories of changes which I made to the Verilog code. The first is that, like the FP class module, the FP mol module is now parameterized. That, of course, is how I made the module support all four IEEE binary floating point formats. When parameterizing the FP mol module, we need almost the same set of parameters. Both FP class and FP mol need the NEXP, NSIG, bias, and emin parameters. The new FP mol module does not need the clog2 NSIG parameter. When parameterizing the FP class module, I discussed but didn't directly use the Emax parameter. If you remember, Emax is defined to have the same value as bias. Because the FP class module didn't use Emax directly, when I needed Emax, I just used bias in its place. In the FP mol module, there are times that the code actually uses the value Emax, so it has been added as a parameter separate from bias. I'm not 100% certain because it's been over 30 years since I've done any programming on VAX computers. But I think that by having both a bias parameter and an Emax parameter, it might be possible to rework the Verilog code to support VAX-style floating point numbers. I don't expect there's much market for that these days, but I could be wrong, and someone out there is just dying to implement the VAX architecture on an FPGA. I could go through each of the lines which need to be changed to use parameters, but it would be very much a repeat of the work I covered in my last video. That is, I think you'd probably find it provided little, if any, new information. There's an additional change I want to make to the code. I've been passing around 6 individual flags for the 6 possible IEEE 754 data types. It would be more convenient to package them together as a bit vector, so I only have to pass around a single quantity which holds all of the flags instead of passing each of the flags individually. The first problem is that I want to avoid using magic numbers. That is, I want to create symbolic names for accessing the individual bits in the bit vector which represent each of the 6 flags. We can easily solve this problem by using parameter statements. This project has 3 separate files: the test bench, the fpmol.v file, and the fpclass.sv file. The problem now becomes, how do we make sure that all of the parameters are defined in exactly the same way in every file which needs them? Verilog is able to include files much like we do when programming in C. I've created a file named IEEE-754-flags.v and added it to the project. You can see the contents of this file on the screen now. Changing from passing around individual flags to passing a flag array is pretty straightforward and can be seen in the last commit in the Git repository for this video. See the directions for extracting this version of the code. Now, since we're using an include file, I suppose we should perform one additional change to the Verilog code. I'm going to move most of the values computed from NEXP and NSIG into the header file. This will help keep the fpclass.sv and fpmol.v modules in sync with each other. However, I'm not going to move the clog2 underscore nsig value into the header file because it's dependent on a function which is supported in System Verilog, but not Verilog. Our header file now contains the code to compute these parameters. Now it's time to test the updated fpmol module. This is going to be quite different from testing the hpmol module. All of the data processed by the hpmol module were 16 bits wide. The exponent field was always 5 bits wide, and the significand field was always 10 bits wide. The old test code reflected this. All of the input and output values for the hpmol underscore tb test module were 16 bits wide. The new test code needs to be a lot more flexible. We need to be able to test input values which are 16, 32, 64, and 128 bits wide. When testing 16-bit floating point values, there are 32 possible exponent values and 1024 possible significand values. When we want to test 32-bit floating point values, we will need to be able to generate test cases for 256 different exponent values and over 8 million different significand values. The problem gets even bigger for the 64 and 128-bit data types. In order to accommodate testing floating point numbers of various sizes, I've gone from writing the test by hand to writing a program which generates appropriate test cases using the number of exponent bits, NEXP, and the number of significand bits, NSIG, as input parameters. The program is a Python script which generates the Verilog test module fp_mol_tb. The Python script takes NEXP and NSIG from its command line. The script also computes the number of test cases it generates based on the size of the exponent and significand fields. That is, when testing 16-bit floating point numbers, the script will generate far fewer test cases than when we wish to test 32, 64, or 128-bit floating point numbers. Here I'd like to inject that I really didn't want to write a separate program to generate the test code. My original plan was to write the test code so that it was completely parameterized and let it run on its own. This wasn't possible because of a problem I ran into iterating over the possible sign bit values. This problem was discussed in a previous video. If you want to have your memory refreshed about the problem I ran into, click on the link shown on your screen now. The code which generates the various test cases is in fp_mol_tb.py. This is a Python 3 script. To generate the version of fpmol_tb.v, which tests IEEE 16-bit floating point numbers, use Python 3 fp_mol_tb.py 5, 10, and redirect the output into fp_mol_tb-16.v. By changing the NEXP and NSIG values, I can generate the code for the other 3 IEEE binary floating point types. I'm using the Vivado tools from Xilinx to develop and test my Verilog code. To test each of the IEEE binary types, I import these 4 files into Vivado and run each of the 4 tests. I'm not done modifying this code yet. There are still lessons to be learned, but the next video is going to be a bit of a palate cleanser. In it, I'll be taking a brief break from writing code to spend a little time programming in FPGA. Until next time, please share this video with friends and colleagues who have an interest in Verilog or floating point processors. Questions and comments are welcome in the comments section. If you found this video useful, please click like below. While you're at it, subscribe to the channel Then click the bell to be notified when new videos are available. Thanks.